Okay, so let's continue. Okay, just remember when a molecule is represented in this way, the wedge is going towards us, the dashed line is going to the back of the plane away from us. So you can look at the molecule in three dimensions. Okay, so another way to represent that without drawing this wedge line and then the dashed line is to draw what you call a Fissure projection. Okay, so if you have this structure, to draw the Fissure projection, you would position the two groups in the vertical position as the bonds that are going towards us. So we place this in this position such that the H and OH are towards us and the CO2H and the CH3 are to the back of the plane. Okay, so let's look at this. Look for an example. Okay, let's say we have this molecule. Okay, obviously this is not chiral, but in order to represent, I'm gonna twist this around. Okay, so you see this two groups. This is OH. This is CH3 above and CH3 below, and then this is carbon connected to nitrogen. So these two bonds you see in the vertical position. So these are the ones that are going towards us. So look, you notice that they are towards us. And these metal groups are going to the back of the line, back of the plane, I mean. So if I draw this, okay, so if I draw the lines would represent above and below. So this will be CH3 groups. And this will be carbon connected to nitrogen. So, and then this will be OH. Okay, so that's what you call Fissure projection. So that's one way to draw or represent a three-dimensional object. Okay, so I'll just clear and then go back to the okay, so this is the representation of the 3D molecule. So the RNS, although this won't be part of any quiz. So the distinction between the two enantiomers, to distinguish the two, there's the label R and S. So it has to do with the way the atomic numbers are arranged relative to the connection to the carbon atom. So it will not be part of any quiz, but so that you know, these are one type of distinguishing one enantiomer from another. So the RNS naming nomenclature. So what are the properties of enantiomer? So this is important, no? So why are we discussing this? Why do you think this is important? So one important implications of these uh, enantiomers and the importance of understanding stereochemistry happened during the 1960s. So there was a misunderstanding of the chemistry behind some chemicals. So they didn't understand stereochemistry back then in the 1960s. There is this sedative, thalidomide, that is a sedative. So it helps pregnant women to it helps treat morning sickness in pregnant women. So when pregnant women take this, they do not feel any morning sickness. Thalidomide. Okay, so scientists or a pharma company tried to mass produce this using chemicals in a large scale production of thalidomide. But what happened after months when the pregnant women gave birth? They began to have children with birth defects. Okay, so it turns out when you do it in the lab, you will not only create the R enantiomer of thalidomide, you also create the S thalidomide. And this one causes the birth defects. Okay, so that's a big fiasco for the scientific community of not understanding stereochemistry. So that is the consequence of that. Okay. Another consequence, you have methamphetamine, which we call shabu, right? Methamphetamine is the one that has physiological effects. So uh, you, the person who takes this will not feel sleepy, will not feel uh, will not be afraid. So that's why in World War II this was given to German soldiers. So that's why they're very efficient soldiers because they were not feeling any fear and they were not able to sleep. So they continue on like having battles for several days in a row without feeling sleepy. So this is methamphetamine. Now, the R enantiomer has no physiological effect that will cause someone to stay not feel asleep or something. So this is actually used in some asthma drugs. So it doesn't have the drug effect like the S methamphetamine has. Okay. Another example is the D dopa and the L dopa. So this is another way of naming enantiomers. I will explain uh, when we go to carbohydrates. You have the D dopa and the L dopa. So the D dopa won't have any biological effect, but this L dopa has been used for the treatment of Parkinson's disease. Another molecule, you have the D-glucose and the L-glucose. So if you watch the video, the D-glucose is the one that is used for the body for energy. So D-glucose is broken down. So you form ATP, you form energy from that. While the L-glucose, although it is sweet, it is not processed by the body. So there was a thought that it can be used as a sugar substitute, but it was so expensive to make, so the idea was discarded. Okay, so D glucose. That's why we call dextrose. The D stands for dextro, and the L stands for lebro. Okay, so that you have two different types of these isomer. as enantiomer. And then you have the S carbone here, that's in caraway seeds, and then spearmint oil. So this is the R configuration. Okay, so here we have an example of enantiomers that have more than one chiral center or more than one carbon with 4 different groups attached to it. So if you draw a mirror, there's a mirror in between this molecule, then it will reflect the other side. But you notice that you cannot superimpose them, then those are enantiomers. Same as these two molecules here, the third and fourth examples, they are enantiomers as well. Now, if you compare these two molecules with the two other molecules, you notice that they have still the same groups attached to themselves, but they are not mirror images of each other. So, what is the relation of these two molecules with these two molecules? They are called diastereomers. Okay, so they are uh, stereoisomers that are not mirror images of each other. So diastereomers are non-mirror image stereoisomers, and this occurs when you have more than one chiral center. Okay, so here you have an example of another example of chiral of diastereomers. So these are mirror images of each other. So these are enantiomers. Wait, why is this not shown? It seems that the image is stuck here. It's not moving. What happened here? Okay, so this is another example of enantiomers. So these are mirror images of each other, 1 and 2, and same with the 3 and 4. But 1 and 4 are diastereomers. Okay, you can also have a molecule that has two chirality centers, but they are not they have symmetry that would make them a chiral. Okay, meaning if you put a mirror in the middle of that molecule, one half will reflect the other half. So look at this molecule. If you put a mirror in the middle, it will reflect the other half. Or if you take the whole molecule and then you make a mirror, the two molecules are superimposable. So basically, they are the same molecules. So these are meso compounds. So these are achiral compounds, basically the same molecule. If you position the Br here on the at the other side of the cyclic structure, so this is a trans configuration. So the mirror image will not be superimposable. So this will make it chiral. Okay. Let's have another example. Okay, this is another example. You have tartaric acid. Take note, if you put a mirror in the middle of that molecule, one half will reflect the other half. Okay, so let's look at this example. So if you have a mirror in between the two, so one will reflect the other, and they are superimposable. So these are meso compounds. However, if you place the OH on the left side of the third carbon, so if you have a mirror, if you draw a mirror there, they will not be superimposable. So these are enantiomers. So these two are enantiomers. These two are identical because they are superimposable. So that's an example of tartaric acid. The groups on the top carbon reflect onto the groups on the bottom carbon. Okay, to summarize, um, isomers are compounds with the same chemical formula but different arrangement of atoms. If you have a structural or constitutional isomer, they have different connectivities. So they're not limited to alkanes. You can have an example where one is an alcohol, another is an ether. You can also have a ester and a carboxylic acid. You can also have the different positions. You have a primary amine and a secondary amine. So they have the same chemical formula. So you have different connectivities there. When you talk about stereoisomers, atoms are connected in the same way, but different three-dimensional arrangement of atoms or groups of atoms. So enantiomers are non-superimposable mirror image isomers, and diastereomers are non-superimposable non-mirror image isomers. So they have more than one chiral center. So the cis and trans isomer, so this E and Z is another nomenclature. We won't go into that, but the cis and trans is an example of a geometric isomer. Okay, so that will be all. So prepare for your quiz for those who have sufficient gadgets. For those who do not have sufficient gadgets, then you'll just have to take the special quiz. Okay, so I'll end it here. I'll give the link to the quiz already.